what are called RCDs, which are residual current devices.
Okay.
So if RCD, yeah. Anyway, over here you guys have got something called a GFCI.
Yes.
Yeah.
Okay. So ground fault indicator. So ultimately what it's doing is it's measuring the amount of current that's going through the circuit, and if it doesn't match, it's going down the earth. So, and that's your fault current. So that's the dangerous shit. So if your earth doesn't work, your chassis of your equipment's going to be live, and then potentially you're going to get a shock off it.
Yep.
So I've had situations where RCDs have become more and more ubiquitous over the last 15 years, and different circuits. It used to be just domestic circuits, and then it became more commercial circuits, and now it's pretty much everything uses them. So, and I've had situations where grandfathered in equipment which doesn't require an RCD has an earth fault of about 7 amps running down the earth, because it's pretty dangerous.
Yeah.
So, and then what you start getting on equipment that then electricians over there don't like RCDs, because circuits get upgraded to them, and then the circuit, they upgrade the circuit, and then it shows the fault. So that then they do the upgrade, and then it's like the heating element of the water heater trips. So then they have to fix but ultimately that was a fault and it should have been fixed.
Yeah.
It's
So
just revealing a problem that's already
Yes,
there.
yeah. And it's ultimately so there was a lot of pushback from them wanting to do this across the board, because it just meant they had more work to do. So, which I don't really care. Like, I'd rather the thing show the fault, fix it before we electrocute someone. So,
Seriously.
so now, what a megameter does is it stresses the insulation of the heating element, solenoid, anything that needs insulation. So, pretty much anything electrical. And so you're applying voltage to 2 points where there shouldn't be a connection to see if you get any connection. So you can do this with your multimeter, but you're only stressing it with 9 volts, roughly, which is what a multimeter can produce. A megameter uses 6 AA batteries. In this case, it uses 6 AA batteries to generate 250, 500 or 1,000 volts. Each megameter is different, so whatever one you end up getting, this is an analog meter with an analog gauge. I like this one, but you can get digital ones, you can get all sorts of ones, you can get ones that measure different, that can produce different voltages. Now, generally, whatever your electrical circuit is, you generally set your megameter to double whatever it is. From my understanding, that means that it's double the sine wave. So for me, we're using 240 volts, so double that, top to bottom of the sine wave is about 500 volts. So we set it to 500.
Okay.
There is potential that you can damage equipment if you use too much voltage. You can actually damage the insulation, but personally, I've never actually done that. When I first got this, I started testing stuff, and I started just going straight to 1,000 because I was like, let's go fucking hard. And it didn't seem to cause any problems. So anyway, 1,000 volts. I'm using 500 today because, well, actually, I don't even know. Is this I imagine it is. So, right. So, stressing the element, doing that sort of stuff. Now, when you're testing the equipment, you want to make sure that it is completely disconnected from the circuit that it's on.
Okay.
So you disconnect the heating, the legs of the element. Now, this one is actually 3 elements in one, because each one of these is its own separate heating element.
Yep.
So if you were just to disconnect the power going to it, and these were all still together, they'd be bridged, which would mean that if you had a small fault on each of them, it would show up as a combined fault across all of them.
Yes. Yeah.
I'll show you that later. It's probably easy to explain.
Any leak is a leak if they're all connected.
Yes, but what you might find is that one element won't trip an RCD, because an RCD trips at 30 milliamps of fault current. Apparently GFCIs trip at 10 or 5 milliamps. So they're sounds like they're more. I don't know a lot about the American side of things, and as you guys are going to start fucking weird, fucking 110, 110 to fucking whatever. But anyway, as these become more and more common, you're going to have to work this out for yourself. But there's just the general gist of how these work. And so what this can do though is when you go to this one, when you go to use it, because it's got batteries in it, you want to make sure that the batteries are fully charged. So you press you set it to battery check, hold the button, and it comes up saying the battery's good. That's the lower gauge on the bottom. So that's telling me it's got plenty of charge. Now, it's got resistance testing here that you can use to test 2 points that you know are connected. So you can test a power cord to make sure that there's not over too much resistance in the cord. I never use that. Like, that's not something which I really deal with. So I can use a multimeter and it'll probably tell me the same sort of thing. So what I want is to set it to 500 volts, and we plug it into the earth connection and the line connection. Doesn't really matter which way around these go, because ultimately we're making a circuit and we're seeing if the circuit works. So put that there. Now we're going to be testing from the terminal to the element leg, or you could test to the flange of the element, because there shouldn't be any connection between these 2 points. Now if there is, then you've got a fault. So do that. If you're doing it one-handed, this meter has a test button which you can push down the lock. Now if I touch these two, the needle goes off the charts because it's there's no resistance. So it's working fine. So then if we go there to there, and the needle goes off the chart because there's a short.
Wow.
Same there to there, short, there to there, short. That's a less of a short though, so we've got less of a fault on that one than we've got on that one. But, and you can sort of see that, like this one actually doesn't look too bad in comparison to the other. And probably the fault is that it's actually melted to, no, that's the, yeah, anyway, thing's pretty cooked. But this would have shown up a fault where the needle doesn't go quite as far, and it might not be tripping an RCD yet, but potentially it will, because the insulation is not going to improve with time.
It's only going to get worse.
Yeah, so when RCDs first came out and I didn't have one of these, I would use the RCD as the test device. So I just go and turn the power on, oh it trips, go unplug everything and start plugging things in one at a time until it trips. And then once it trips, then I'm like, oh, it's that solenoid, or it's that heating element, or it's that whatever. But then the trick that you can run into there is sometimes the fault that you've got might not be displaying all the time. So you get what's called nuisance faults, where the heating element is heating up, and I get nervous when lots of cameras go on me. So,
Scott, do you want me to ask a question?
no, I just think we're all bears. So the heating element heats up, and so as the element heats up, metal expands and water gets into the joint, and then can cause a trip. So when it causes, so you might find that something doesn't show a fault when it's dry or not hot. So there was an element that we took to the training the other day that was faulting an RCD for me, and it faulted when I tested it back in Australia. We get it here, it's dried out, and it was showing no fault. So that's just something to be aware of as well. But the other thing that can happen is that if I was doing it before I used this, and I was just manually unplugging and plugging things in until it trips, what might have happened is that one solenoid might have had a small fault, and then I plug a second solenoid in which has a small fault, and collectively they are enough to trip the breaker at 30 milliamps. But by themselves they weren't. So then I'll look at the first one and say, that's my problem, I replace it and it's all good, until the other one kicks the bed and does the same thing, and then it trips again. So that's where it's better to be able to go through and test everything with that and go, oh, I've got a small fault there and a small fault there, I'll replace both of them instead of just doing one.
Super valuable.
Yeah. So
That element was fine, right?
no, it's perfect. Yeah.
Great solid.
It was working fine without an RCD. So, but yeah.
Can I ask a question?
Yeah, of course.
So when would you choose between using this or like checking continuity or resistance?
I just use this.
Okay.
You just skip the whole continuity thing?
So when you're saying continuity, are you talking about from the resistance of the element?
Just
or are you
completing
talking
a
about from there to
circuit.
there?
So continuity, you're just gonna like you could have this completely faulted out, but still have continuity technically, as long as that inner coil is all connected.
Yeah.
Right.
Yeah.
Yeah, and then you would
But then-
check the
but then your
resistance.
resistance is
Yeah.
where we typically find those faults.
Ah.
But the issue is the power that produces versus our meters at 9 volts. That's putting out 500 volts or 1,000 volts. It's forcing that fault.
Yeah.
Yeah.
It's saying like
Oh,
it's
okay.
like hairline
Where-
tiny,
Okay.
where we might not pick it up on a traditional meter.
Yeah.
Okay.
This
I
is
don't think
like,
I realized
bam.
that was how meters worked.
Yeah.
Yeah.
right.
Okay. Got
Yeah,
it.
it's pushing that 9 volts to find
Okay.
the fault.
And that's
Okay.
where
Okay.
nuisance faults are what used to really piss me off. Is
Yeah.
I'd go and I'd be it's tripping the breaker, and we've got things called combo breakers in Australia. So it's a 20 amp RCD all in one. So you don't know if it's tripping because it's going over 20 amps or if it's going over 30 milliamps of fault current.
Okay.
So you don't. So this
Yeah.
is where you can sort of work out, and then I can go to that and say, oh, it's not tripping with 500 volts. Maybe I'm going over amps, and then you can amp clamp and test. No, I'm not going over amps.
Yeah.
So then you might actually have a faulty breaker.
Okay.
So
Yeah,
it
yeah,
might
yeah.
be, and there's been a couple of times where I've tested everything, and then I've gone to the Sparky, and I'm like, look, mate, I think the breaker's
Electrician.
buggered. Yeah, Sparky. Yeah, okay, thank you. And then the Sparky comes in, and he's like, oh, that never happens, and I'm like, well, fuck, I think it is, and then he'll change the breaker out, and then that fixes it.
Yeah.
Thanks, man.
Yeah.
I think though, if you tell an electrician here that it's because we have a similar thing. It's not the RCD, but
Yeah.
it's the what do you call them?
It's off.
Yeah, GFCI that they're starting to put in new breakers, new construction stuff. But I mean, if you can pull out one of these and be like,
Yeah.
do you have one of these on your truck? This is showing,
Yeah.
like we're fine.
It's
on
leveling
everything
us.
else.
Yeah.
Yeah, and it's trying to stay ahead of the curve, and that's where, and you don't look as Mickey Mouse when you're going backwards and forwards to a breaker, like going, oh, it's still tripped. Oh, no, that wasn't it. Oh, tripped again. Oh, and especially when the breaker's like at the other end of the building as well, and you're
Yeah.
like,
Yeah.
yeah. So jump in and have a go.
What are they called?
GFCIs.
GFCIs. I've only seen those on like 110.
They're
Very uncommon on 2.
It is uncommon, but it is more and more.
Okay. Okay.
So I've seen them in Washington State.
Okay. Got it. Got it.
I was going to say, Rachel, I don't think that's something we're really going to run into for a while right now.
Yeah, so you
Like
can also put it
GFCIs
like
on
right
2.
on the flange.
Yeah. So
Yeah, because it's not going to be out of your machine.
would there be a time